Never change the running session.
Okay, welcome to the first session with the regular papers that we have. So first it will be Mario Gleirscher from Bremen, University of Bremen, talking about probabilistic risk assessment of obstacle detection in grade of automation for freight trains.
Yeah, hello, good morning everyone. Thank you for being here and thank you for the opportunity to present some partly ongoing work on risk assessment, risk quantification. Hold on. Yeah. Okay, can you hear me now?
It's not on these speakers, it's for the
Okay. I'm sorry. Right. Does anybody of you know what GoA 4 is? I didn't know until just before I completed the risk assessment. The joke is because the risk assessment is, I'm going to just give a brief overview of what we did on one slide. Is about, so we had the problem of identifying the false negative rate of a fault-tolerant train sensor and reduce it to an acceptable level. False negative means the sensor is supposed to detect something but can't or missed an object. In that case, it was a setting train's obstacle detection, and the sensors are supposed to detect obstacles on the railway track, and with a certain probability they fail to detect existing obstacles, and this is what we call false negative. And the study was all about figuring out for a particular architecture, which you see here. A little small. I'm sorry for the slide. Should be a little larger. Anyway, it's a two-channel sensor system with two duplicated channels with a sensor component and a perception component, and using the standard voting pattern to decide whether to switch off, or whether to emergency brake the train or not. On the basis whether both channels deliver consistent results. This is a fairly standard architecture used in many systems where reliability and fault tolerance plays a role. And what we approached that risk assessment in the context of highly automated or autonomous train systems, like used perhaps in the future, if we want to believe what people say, on shunting yards where trains are supposed to run around autonomously, and there is a certain upper threshold for the false negative rate that is to be applied according to applicable standards in the railway domain. So what is usually be done is what we also did. We performed a fault tree analysis of the whole sensor module, and in the course of this fault tree analysis, we of course had to estimate component error rates, and in order to figure out to quantify the basic events in the fault tree. For that, we decided to use a stochastic model. In our case, it was a continuous time Markov chain model, and that we used to estimate these error rates, to estimate the overall, the top level events and the intermediate events of the fault tree. And also what we did is then to use parametric model checking to generalize our stochastic model a little. Our contribution is basically a procedure, a guidance for engineers in practice, like for instance working with Alstom or Siemens, telling them, look, if you want to do your risk assessment for your train sensor system, then you could take our procedure as a template, and using fault tree analysis in a specific combination with parametric model checking of Markov chains. It is not a result, a disclaimer, a big important thing. So we do not, it was actually highlighted by the reviewers, so we should really make this clear. We do not say that we managed to prove that the resulting false negative rate is actually below the accepted threshold, and that means that trains can in the future be certified according to this result. We can just say we have a procedure that allows you to do that, and then you need to decide whether the parameters you've used when applying this procedure reflect the reality in your particular setting. Yeah. This is always the key question in certification. Certification applies on a case-by-case basis. And in other cases, certification needs to be redone. Yeah. So, okay. Let me quickly walk you through some definitions. We use often the OD abbreviation for rail obstacle detector. It's nothing else than a sensor system. And we have a lambda OD as the obstacle occurrence rate, the rate how often the obstacle occurs in a particular time unit, for instance hours. And then we have an event obstacle present but undetected. This is our hazard or false negative. And what we are interested in is the probability of our hazard, P of HOD. And then it's also important to distinguish the probability of a single HOD from the rate. So that this is a different view. So with the rate you get based on a particular obstacle occurrence rate, the rate of the false negative occurring. And this rate, this is subject of our risk quantification, is to be compared with the tolerated or tolerable rate, which in our case was chosen to be 10 to the minus 7 according to feedback from a guy from Siemens as responsible or involved in the certification process for particular such systems. What I'm presenting you in the rest of the talk is I'm giving you an insight into how we constructed the fault tree, and how we estimated some of the error probabilities of some basic events in the fault tree. I'll give a very brief insight into how the stochastic model looks like and how we identified the probability of the hazard. And finally, an idea on what we did to actually push the hazard rate below this threshold level. So as you can of course see, this is a very practical work. So this is just hands-on work for risk assessment engineers in practice. There's from a research point of view, we apply methods. So this is not a presentation of a new method, of course. Yeah. So I don't want to align your expectations. Nevertheless, so we were not given a particular sensor architecture and implementation. All this is under the hood and it was not accessible to us. So we had nothing more than the block diagram I showed you before. Basically something that everyone could do at home. And based on that, sorry for the small font, we identified certain, we split down we analyzed the failure possibilities of that two-channel module that would lead to our hazard. On top is nothing else than the hazard, the false negative. And then there are several domains where false can result, namely the two channels could provide a contradictory result and the voter doesn't see it. This is a typical proof or verification obligation for such a fault tolerance pattern. Then there could be a systematic voter fault, so independent of whether the channels are consistent or contradictory, the voter could just systematically err. And also in this part of the fault tree, it's basically about there are consistent channels, so they both provide the same result, but it's consistently wrong. Yeah. So this is also something that the voter can't detect, because it has only two channels at hand. Right? And this simultaneous failure can occur in the sensing. Sorry, I would like to point in the sensing component, in the perception component, and also in the communication subsystem within this module. So it's a very straightforward breakdown, as you can see. And everything that happens below there is then detailed for the perception component, which, according to our assumption, is the most complicated, most complex component of these of the sensor system, because in the perception component we assume that there are neural networks, convolutional neural networks used, for instance, to do the obstacle detection, at least in one channel, while the second channel can still be based on conventional techniques like simple camera-based optical edge detection and stuff like that, that has been used for a long time for such things. So and then this is why this simultaneous perception failure, the unsafe failure, breaks down into a fraction which is associated with a neural network based system for obstacle detection, and the other one is associated with a conventional perception system used. Okay, I'm going a little into the details on how we tried to estimate the basic event probability for the perception fault in the case that for the perception fault. That means in that particular case for the neural network based channel, so we tried to figure out what is the residual probability of the neural network not to detect an obstacle when it's there. Yeah. And there's a couple of this is ongoing work actually, which or at that point when we wrote this paper, this was ongoing work, which is why the details in our paper are only quite partial. But in the meantime, my co-authors managed to get a more detailed paper accepted. It's in the slides. I can also share the citation for you. The whole neural network is so what we did is we built up a mathematical model of the neural network. So we assumed that there is an image database with known obstacles as a subset, and we assume that there can be a metric that gives us information on the equivalence of two images of that database. Yeah, there's a lot of formulas, but essentially it means for two images, we say they are equivalent if that particular metric tells us that they are null connected. So the difference between the metrics for both pictures, so there's no difference between the metric for both pictures. And then they are in the same equivalence class. We further assume that we have a number I of such equivalence classes, and that the probability of an image drawn from a particular equivalence class is also known, symbolized with pi. And what we then do in order to finally identify the misclassification error probability, or the probability of a false negative of the neural network, is we apply the coupon collector problem. The coupon collector problem basically uses a central random variable which models the number of draws I'd need, draws of images from the database I would need to cover the existing equivalence classes. Yeah. So you would just, in one simulation run, you would constantly draw images from your database, apply it to the neural network, and then stop if the neural network has seen and correctly classified at least one image in each of the distinguished classes, right? And then you get sort of a coverage. Yeah. And the coupon collector problem allows you to provide a distribution for this random variable. Because this is not analytically solvable, such problems are typically approached with a Monte Carlo simulation. And this is what has been done before, of course, but this is also applicable here, where you eventually get some probability of, for 5 minutes to go. Okay.
We started a bit late.
Okay, I will rush through because this is actually perhaps something that because of the workshop I was wondering whether I could rush through a little more. I think the main result of this slide, which contains quite a number of intricate details, the main message is so we use the coupon collector problem to figure out the probability that the neural network misses one equivalence class, and also incrementally reduce this error probability, this misclassification probability, by adding increasingly many equivalence classes to the original set. So this is a mathematical framework. Yeah, there's currently no big enough database. That's also important to say, which captures enough pictures, but it's straightforward if the train domain starts selecting and collecting such images. Eventually, we get at least a notion of error probability, an upper bound for this error probability, and what we then need in the fault tree is just to choose an error probability that is bigger than the upper bound. Yeah. So conservatively choose an error probability for the basic event, and this allows us to then go further in the fault tree. So what we did is now we managed to mathematically inform us about the upper bound of that error probability, and we choose a larger one. We do a similar mathematical reasoning for the other basic events. Also, we use a chi-square test to actually test whether the channels are diverse enough that that their error probabilities are stochastically independent. This is an important check because otherwise the fault tree is invalid. Yeah, so not even important to understand what is on the slide. For a fault tree, it's important that all the basic events are stochastically independent in order for the composition of the fault tree to work properly. That's what we also did. And now you might ask the question, where do we get the information for the top level event? So we encoded all the basic events we prepared the stochastic model of the processing of the sensor system, inserted all the estimated basic event probabilities, and then this is a CTMC, a continuous time Markov chain. It allows us to then get an estimate of the top level event, namely the false negative rate of the module. And because it's a parametric analysis, we can use a range for the basic event probabilities, and then we get a range for the top level event probabilities. That's the key point, really, that we manage. So the model is a template that can be reused in a wide variety of settings. And that already brings me almost to the end of my talk. We managed to then use two of these modules that I've shown and combine our analysis in order to reach below these 10 to the minus 7 tolerated hazard rate. So we actually need basically two such sensor systems in order for current certification requirements to be fulfilled. This is really the key takeaway, I think, for you. So we have a procedure where you can stepwise work towards this goal, achieving the tolerable hazard rate for such a system. Yeah. I've said all this, and again, coming back to at the beginning of my talk, the grade of automation 4 plays no role in this whole thing. Because we tell you, if you have a sensor system somewhere in your garden or in an autonomous train, we tell you how you can achieve a tolerable hazard rate or not achieve it. Thank you very much for the questions.
Thank you. Any questions? Yes. Yeah. Thanks for the talk. Sorry. Yes. Thanks for the talk. You said this is very applied and you're not proposing a new method, but perhaps can you comment on where are limitations of the existing methods that you used that you had to work around? So what should be improved in the existing methods?
Unfortunately, that's a bad answer. There are no limitations on the existing probabilistic model checking methods that came in our way when we did the analysis, but there are limitations on the ways of how to construct an image database and to select these image equivalence classes. This is discussed in another paper, but also it depends on the practitioners delivering these images, right?
Okay, so this whole pre-processing where you actually did simulation instead of model checking is not because of a limitation in Prism or something?
No.
Okay.
No, this is something different. That is also hidden. It's a very important question, by the way. So when you see at this Prism model, for instance, we use what we estimated with the Markov chain, with the Monte Carlo analysis. We use it just as a parameter here. So it's basically done outside the model. And then we assume that the parameter is properly estimated, and this gives more confidence in the overall model. Yeah. So this is why I say that was not a problem. Yeah. I was sorry. I just wanted to keep eyesight.
That answers my question.
Thank you.
Any more questions? So
So I didn't get exactly, so this is methodology, but has it or has it not been applied to, I understood it has not been applied to some kind of real system, you just had a very brief outline. Yeah, can just, so it has not basically, just a sort of method which has not been applied to a real system, right?
It has not been applied to a real system in the sense that Siemens, for instance, asked us to apply it, but we were in touch with Siemens and they confirmed that this should perhaps be the way how to do it if we were asked to certify a train in the near future. And they gave us some numbers for some of the parameters we are using in the fault tree, particularly the tolerable hazard rate. Yeah.
So you also mentioned that there is a paper, follow-up paper on this, so then you have a point there. Yeah.
So this is the
Cyril, can you,
the first one. It's just been included in the Festschrift for Werner Damm. So this is the paper that explains a little more how we construct, how we abstract the neural network using Riemannian manifolds and degenerate metrics on Riemannian manifolds, and further in order to construct the equivalence classes. And then once you have constructed the equivalence classes, then you can work with the Monte Carlo simulation that I've shown to you. But there's a lot more than it is not discussed in the paper. Yeah, of course. If it's allowed.
You said this has been done and you consulted some people from Siemens and so on. Does this mean the model cannot be published, or would this be available?
No, the model unfortunately can be published because I have crafted it, and we were just asking them for the parameters that I was using in the model. And there's no non-disclosure agreement. So if you like, you can have it.
Perfect, thanks.
Yeah.
Okay, let's thank the speaker again.